Welcome back to our series on probability theory. I'm Mark Ledbetter. This is lecture video 37, part 8A, and we are in the continuous bivariate distribution section. This is actually section 4.4 in the book, and I am doing this before I do the conditional distributions because I want to cover the conditional distributions for both discrete and continuous at the same time. I like doing it better that way. So in the previous lecture video series, we talked about correlation. We talked about the properties of covariance, the properties of the correlation coefficient. We also talked about the least squares line, and in our last video, we did an example that took almost all of these calculations into consideration. So, in this section, we are going to talk about the continuous bivariate distributions, and we're going to compare them to the discrete bivariate random variables as well. So I want to cover the joint range of x and y, the PDF, the properties of the PDF, marginal distributions, independence, and correlation and regression. So basically, we're going to cover everything about the discrete the continuous distributions that we've covered now for the discrete. So let's get started. So remember that for continuous distributions, we use the term PDF, probability distribution function, and for discrete random variables, we use the probability mass function, so PMF. So consider an experiment with sample space S, and we want to let x and y be two continuous random variables defined on S. Then the joint range or support of x and y together is given by, we'll call it R, capital R. So the set of xy, or the set of the points xy, such that x of w, or omega is the letter we actually use, but we'll say W for this course, that's fine. So x of W and y of W. These are random variables. And recall that random variables are functions, and they take the elements of the sample space and they convert them to real numbers. Okay, and sometimes the random variables act as a identity function. So if we have values of heights, we may leave them as heights. We may not translate them or do anything. But if we have something, let's say like gender, then we will have to take that name, male, female, and translate that to a number. And so that is what a random variable does, just as a reminder. So we have the point x of w, y of w, where w is in S. And so this is the joint range. It seems like this is trivial, but this is one of the most important things that we can do and that we need in order to be successful at problems in this section. Okay, so this joint range or support of x and y is actually very important because we're going to integrate, and double integration. Integration requires that you look at your direction of integration and your space to see if you need to break up the integral into more than one part. So the joint PDF of x and y is an integrable function, f of xy, such that, and here are the properties. And I wanted to, and I forgot to write it over here, but I did write PMF, so this means discrete. Okay. So we have continuous here, and we have discrete over here. And so the properties are, we can integrate f of xy of dy dx from negative infinity to positive infinity, both x and y, and that had best add up to 1 or integrate to 1. So the area under the PDF in both x and y and in z, so remember that z, you can think of the z dimension or the third dimension equals f of xy. So the integral of f of xy is a volume that has to equal 1 on the xyz plane. So a marginal distribution of x would be f of x, and we integrate f of xy over y, so dy, and so in the space of x we're going to denote it as s of x. And so for the PMF, remember that for property 1 here, we did a double summation across x and y of fx and y, and then that sum had to be 1. And for the marginal, we use the same notation. We would sum across y, and again, we would denote the space as s of x. For the marginal distribution of y, f of y, we're going to integrate with respect to x, and the space of y is s of y. For a discrete, we would sum across x and use the same notation for the space of y. And again, we have a parallel between the continuous and the discrete. Let's say that B is a subset of our sample space S. Then for the continuous case, the probability that x and y are in B is we integrate across all of those x and y that are in B of f of x dx dy. And for the discrete case, we summed across the values of x and y in B. And so these are parallel concepts. So I wanted you to see the relationship and the symmetry, if you will, between the two. So property number 4 here implies that the probability that xy is in B is the volume of a solid over the region B in the xy plane, and it's bounded by the surface z equals f of xy. This is an important concept, especially with some of the homework problems, all right, in this section. So to get them, you have to be aware that you're in the third dimension for z. You're calculating a volume of the solid over that region B, which is the joint range of x and y that you need to find. So let's do our first example here for continuous. F of xy is going to be x plus y if x is between 0 and 1 and y is between 0 and 1, and it's 0 otherwise. So A, we want to find the marginals. But before we do anything, we have to find this joint range of x and y. So yes, you need to graph. This is the first step, is to graph. And this one is easy. We're going to call R the shaded region here. Remember, x goes between 0 and 1, and y goes between 0 and 1. When we draw it out, we get a rectangle. Okay? So remember that for independence, we need a rectangle for the joint space of x and y, and the joint PDF has to be equal to the product of the marginal PDFs. So let's find, so here is R written out in set notation, the set of x and y such that x is between 0 and 1, y is between 0 and 1. And then the marginal is going to be the integral of f of xy dy. And the limits of integration are easy here. They're between 0 and 1. So we substitute in x plus y. Remember that we're only integrating with respect to y. So we end up with xy plus 1/2 y squared. And it's not a bad habit to get in, hint, hint, to write which variable you're substituting in, because you usually have more than one. So I like to write y equals 0 to y equals 1. Then I know I'm plugging in for y, not for x. And so we're left with x plus 1/2. And don't forget your space of x, your range of x. And then our third step is to find the marginal of y. And so again, it's the integral with respect to x from 0 to 1 in this case. And we get 1/2 plus y, and y is between 0 and 1. Now, we can verify that these marginals are in fact marginals. Integrate f of x dx across the range of x, and so we have x plus 1/2, which integrates to 1/2 x squared plus 1/2 x. From 0 to 1, we get 1/2 plus 1/2, which is 1, and very similar for f of y. Now, are x and y independent? So when I look at f of xy, remember, is equal to x plus y when it's defined. And there's no way that you can take this and make it a product of two functions, one of only x and one of only y, that I'm aware of. And so, not in the real numbers. And so, but we can use the definition here, and we can take the product of the marginals, which is given here, x plus a half times y plus a half, which gives us this expression, which is certainly not equal to x plus y. So x and y are not independent, or you could say x and y are dependent. So even though the space of xy is a rectangle, x and y are not independent. That's only part of what we need to know in order to determine if x and y are dependent or independent. Okay, so we want to find the mean of x and the mean of y. So I want to recall for you or remind you that if we set u of 1 of xy equal to x, then the expected value of u1 is equal to the mean of x. So I can integrate this. So the expectation of u1 times f of xy, and then I have to integrate over x and y. And so substituting in for my limits of integration, I have this, and then I substitute in for f of x and y, f of xy, and multiply out. I get x squared plus xy. I take the integral inside, which is respect to x, and I end up with 1/3 x cubed plus 1/2 x squared y, and again, x from 0 to 1, and I still have dy out there. So this is really in the middle. So we have to solve that before we can integrate. And so we end up with 1/3 plus 1/2 y dy, which gives us 1/3 y plus 1/4 y squared from 0 to 1. A third plus a fourth give us 7/12. It's very similar, almost identical for mu of x, and we get 7/12, or let's see, I'm sorry, this is the alternate way of doing it. So instead of using the joint PDF, I use the marginal PDF, and of course I get the same answer. And for the mean of y, I did this using the marginal, and I end up getting the same answer, 7/12. You can't count on that. Obviously, you don't always get the same answer. So now we want to find the variance of x and the variance of y. So to do that, our first step is to find ex squared and ey squared. So remember that by the definition, that we take x squared times, now I could use the marginal, f of x, but I've decided to use the joint here just to show you how that's done as well. So x squared times the joint PDF over dx dy. And, oh, I'm sorry, so I actually plugged in, said it's also equal to the integral of x squared times the marginal, and that was easier. So we multiply x squared times the marginal, we get x cubed plus 1/2 x squared. We integrate that, we get 1/4 x to the 4th plus 1/6 x cubed from 0 to 1, and that gives us a 4th plus a 6th. And if we get a common denominator of 12, that gives us 5/12 for ex. And we do a similar process, but using the marginal of y, and we end up with 5/12 for e of y squared too. And then we plug in for the variance using this formula, ex squared minus ex quantity squared. Now you notice I did this in steps. I didn't try to do this as an integral. I really don't recommend that you try doing this whole thing as an integral, because it's so easy to mess up and to make a mistake. I do suggest that you do this as two parts. And it also makes it easier for me to grade, but really the reason for me suggesting it is so that you don't make a mistake. It's very easy to make a small mistake and get the answer very wrong. And so when we work through this and substitute in, we get 11 over 1/44 for both the variance of x and the variance of y. All right, so there's our first example. Please don't forget to scan and upload your lecture notes before midnight of the date listed on the course calendar. If you have questions, please come to our virtual office hours, and I am happy to help you. And if you can't make it to that, then you're certainly welcome to email me, but please send me both a picture of your work and a picture of your problem so I can help you quickly through email. Take care of yourself and stay safe until next time. We'll see you then.